Section: Introduction. In this section, we explore the potential of large language models, LLMs, as decision-making agents capable of handling complex tasks independently, such as web navigation, device control, code writing, and personal assistance. To excel in tasks requiring a series of decisions, these agents must optimize for specific multi-turn objectives, like success rates, rather than just mimicking the most likely action at each step, which is what they learn during pre-training. While we could apply successful single-turn reinforcement learning from human feedback (RLHF) methods, such as RAFT, DPO, and PPO, these do not effectively assign credit across multiple turns, leading to high variance and inefficiency in learning. Alternatively, we could use value function learning methods like TD learning, but this requires additional training that may not generalize well with limited data. To tackle this issue, we recognize the need for a benchmark that validates multi-turn RL algorithms for realistic LLM agents. This benchmark should meet three criteria: diverse tasks for training, sufficient complexity to challenge reasoning abilities, and minimal engineering effort for quick prototyping. However, existing benchmarks fail to meet all these criteria. Our first contribution is the development of the Collaborative Agent Benchmark, Kernel Bench, aimed at supporting research on multi-turn RL algorithms in realistic scenarios. This benchmark focuses on artifact creation, where agents must collaborate with humans to produce artifacts like code or web pages that meet expectations. The agents need to understand human intent and fill in gaps with limited information. To enable rapid evaluation, we use LLMs as human simulators and provide ground truth artifacts for accurate responses. We also created evaluators to measure how closely the agent's output matches the ground truth. For effective credit assignment in multi-turn RL, agents must navigate partially observable environments where not all relevant information is visible. They should be rewarded for seeking information, especially when data is scarce during fine-tuning. We suggest that additional training time information, like final outcomes, can help with credit assignments. Our second contribution is Sweet RL, a straightforward yet effective RL algorithm that enhances credit assignments by providing the critic with training time information that the actor does not have. This approach allows us to learn the advantage function directly, which assesses the effectiveness of actions without needing to first train a value function. We parameterize the advantage function using the mean log probability of actions and train it through the Bradley-Terry objective at the trajectory level. This method aligns better with pre-trained LLMs than traditional value head training, resulting in improved generalization. In our experiments, we find that using asymmetric information during training and appropriate learning objectives leads to a more effective multi-turn agent in realistic tasks from Kernel Bench, achieving significant gains in success and win rates compared to state-of-the-art algorithms. Consequently, the performance of LLAM A3.1 to 8b can match or even exceed that of leading proprietary models like GPT-4o and o1 Mini. Section Summary. In this section, we discuss the potential of large language models, LLMs, as autonomous decision-making agents and highlight the challenges in optimizing multi-turn decision-making tasks. We introduce the Collaborative Agent Benchmark, Kernel Bench, to evaluate multi-turn reinforcement learning algorithms and present our novel Sweet RL algorithm, which enhances credit assignment by leveraging training time information, resulting in improved performance on complex tasks compared to existing methods. Section: Related Work. In this section, we discuss the foundational design principles of our Collaborative Agent Benchmark, or Kernel Bench, aimed at tackling the challenges of developing multi-turn reinforcement learning algorithms for LLM agents. We will also explain two specific tasks: back-end programming and front-end design. Our first design principle emphasizes sufficient task complexity to challenge the reasoning and generalization abilities of agents. Since our goal is to enable LLM agents to perform tasks in real-world scenarios, the benchmark must reflect realistic challenges. Kernel Bench is structured around artifact creation tasks, where collaboration aims to produce tangible outputs like code or web pages. To succeed, Agents must understand the intricacies of code and visual design, especially when faced with unfamiliar requests or less than ideal collaborators. The second principle focuses on minimizing overhead for rapid research prototyping. Each collaboration task is designed to recreate a specific reference artifact, allowing an LLM to simulate a human collaborator effectively. This setup enables the LLM to address uncertainties accurately. Additionally, having a reference artifact allows us to use objective evaluation metrics to measure how closely the final product matches the reference. Setting up Kernel Bench requires only API access for LLM calls and some Python packages for code execution and HTML rendering. While real human collaborators may only have a general idea of the desired outcome, using a clear reference artifact enhances reliability. Our third principle ensures sufficient task diversity for reinforcement learning training without overfitting. Given that top LLMs are trained on vast datasets, it's crucial for our benchmark to include a variety of tasks to assess the scalability of different multi-turn RL algorithms while maintaining reliable simulation and evaluation. We designed Kernel Bench to be highly scalable, featuring over 10,000 procedurally generated tasks, which can be expanded by adding more existing artifacts like code and web pages. The difficulty of Kernel Bench can be adjusted by creating more complex collaboration tasks. Next, we will detail the setups for Kernel Bench, including back-end programming and front-end design. Section Summary. In this section, we introduce Kernel Bench, a benchmark designed to facilitate research in multi-turn reinforcement learning (RL) algorithms for LLM agents, focusing on reasoning-intensive tasks like artifact creation. We outline its foundational design principles, which emphasize task complexity, minimal overhead for rapid prototyping, and sufficient diversity to prevent overfitting, ultimately enabling effective evaluation and scalability of RL approaches. Section: Back-end Programming Collaborations. In this section, we describe our back-end and front-end programming collaborations. For the back-end programming task, we work with a human simulator to create a custom Python function, limited to 50 lines. Initially, we receive a general description and the function's signature, but we must identify missing details, such as specific conditions and edge cases. We ask the human simulator clarifying questions, who responds with brief explanations based on reference code they can see, but they do not write any code. Our interaction is capped at 10 exchanges, concluding when we either present our final solution or reach the maximum rounds. Our success is measured by passing 10 hidden unit tests for the function, with a binary reward given only at the end. For the front-end design task, we collaborate with the human simulator to design a web page by writing an HTML snippet of about 100 lines. We start with a high-level description, but many specifics, like layout and color choices, are only visible to the human simulator. We write HTML solutions that are rendered in a web browser, allowing the human simulator to compare our output with a reference page and point out differences. Similar to the back-end task, we have 10 rounds of interaction, and our performance is evaluated based on the similarity of our design to the reference page, with a reward score ranging from 0 to 1 given at the end. Next, we introduce our method, SuiteRL, which involves a two-stage training process for reinforcement learning. We define our problem setup as a finite horizon partially observable Markov decision process, where we have observable and hidden state components. At the start of each episode, we receive an initial instruction and some hidden training time information, which remains constant throughout. During each turn, we consider the entire interaction history to decide our next action, which consists of a sequence of tokens. After our action, the user responds, updating our state based on the latest interaction. We aim to maximize cumulative rewards throughout the episode, learning from past interactions rather than relying on costly real-time human interactions. We model the expected rewards and advantages of our actions to refine our policy for generating responses. Section Summary. In this section, we describe two collaborative tasks where an agent works with a human simulator. One involves writing a Python function based on high-level descriptions and clarifications, while the other focuses on designing a web page using HTML snippets. Both tasks are limited to 10 interaction rounds, with success evaluated through unit tests for the Python function and cosine similarity for the web page design. Section: Learning Turn-Wise Advantage Functions. In this section, we explore learning turn-wise advantage functions to improve credit assignments in reasoning-intensive tasks. Previous studies have attempted to learn a value function first and then derive the advantages of individual actions from it. However, we found that these value functions struggle to generalize well when we have only a few samples for fine-tuning, as discussed in our earlier section. We believe this difficulty arises because accurately learning a value function in such tasks is challenging and does not leverage the reasoning and generalization strengths of pre-trained large language models, LLMs. Instead, we propose directly learning the advantage function for each action taken at each turn. Drawing inspiration from successful preference optimization in fine-tuning LLMs, we suggest training the turn-wise advantage function using pairs of trajectories. For two trajectories under the same task, we label them as chosen or rejected based on their cumulative rewards. This allows us to use the Bradley-Terry objective for fine-tuning, where we adjust the advantage for actions in the chosen trajectory upwards and those in the rejected trajectory downwards. To align our learning objective with the pre-training of next token prediction, we parameterize the advantage function by reusing the existing language model head of the LLM. We find it crucial to normalize the advantage by the length of the response to stabilize training. Our key observation is that while our final policy cannot access hidden information, this information is available during training. The advantage LLM can utilize this hidden information to better assess whether the actions taken by the policy are appropriate. Thus, we provide additional training time information to the turn-wise advantage function while only giving the policy the interaction history, creating an asymmetric actor-critic structure. We can apply any successful algorithm from the reinforcement learning from human feedback (RLHF) literature to optimize the per-turn policy, treating interaction histories as prompts and the turn-wise advantage function as the reward model. During this training phase, we do not require human collaborator input. For simplicity, we choose to use direct preference optimization (DPO) for training. In our experiments, we aim to validate the effectiveness of SuiteRL as a multi-turn reinforcement learning algorithm for training LLM agents in complex collaborative tasks. We focus on several questions, including how existing generalist models and multi-turn RL algorithms perform on collaborative tasks, how SuiteRL compares with state-of-the-art (SOTA) algorithms, the impact of asymmetric information on credit assignments, the best algorithmic choices for leveraging LLM capabilities, and how SuiteRL scales with increasing training samples. For our experimental setup, we compare SuiteRL against various SOTA LLMs and multi-turn RL algorithms on the kernel bench platform. We include LLAMA 3.1 to 8b instruct and LLAMA 3.1 to 70b instruct as examples of SOTA open-source LLMs, and GPT-4o and o1 mini as examples of proprietary LLMs. We evaluate these models in both single-turn and collaborative settings to see how LLM agents benefit from multi-turn interactions. We also consider a simple baseline called rejection fine-tuning, which minimizes negative log likelihood loss on successful trajectories. Additionally, we look at a recent baseline called multi-turn DPO, which constructs contrastive trajectory pairs and optimizes the policy directly without a critic. SuiteRL first trains a turn-wise advantage model with access to training time information and then optimizes the policy based on the rewards from this model. Our experiments focus on learning from previously collected data, as online human collaboration data can be costly and requires extensive annotations. For evaluation, we measure the average percentage of unit tests passed in back-end programming tasks and the average cosine similarity of final web pages to reference pages in front-end design tasks. We also include a win rate metric against GPT-4o, where the model producing a web page closer to the reference wins for each task. Section Summary. In this section, we propose a method for learning turn-wise advantage functions to improve credit assignment in reasoning-intensive tasks, as prior value function approaches struggled with generalization due to limited samples. We introduce a training framework that utilizes preference pairs of trajectories to optimize the advantage function, enabling our multi-turn RL algorithm, SuiteRL, to effectively leverage hidden training time information for better policy optimization in collaborative tasks. Section: Comparisons on Kernel Bench. In this section, we present the performance comparisons of various state-of-the-art large language models, LLMs, and multi-turn reinforcement learning, RL, algorithms on different tasks using Kernel Bench. We observe that multi-turn collaborations significantly improve the performance of LLM agents in creating artifacts, as they better align the final output with human expectations. For instance, when tasked with producing a final product in a single turn, even the top-performing model, GPT-4o, achieves only 16.2%. However, when given multiple turns to interact with human simulators, the success rates for all models double, such as LLM A3.1 to 8b instruct increasing from 6.9% to 22.4%. Despite these improvements, multi-turn collaboration remains difficult, with GPT-4o and o1 Mini achieving success rates of only 40.4% and 30.3%, respectively. Although o1 Mini shows progress in symbolic reasoning tasks like math and coding, these gains do not translate into better strategies for multi-turn collaboration, indicating that further fine-tuning is necessary for LLMs to optimize human interaction. Next, we compare other algorithms with SuiteRL. After fine-tuning with downstream data, even the simplest RL algorithm, rejection fine-tuning, shows improvements in performance, with increases of 5.8% in back-end programming success and 4.8% in front-end design win rates. However, we find that rejection fine-tuning often leads the LLM to memorize specific solutions rather than develop a generalizable strategy for new tasks. While multi-turn DPO addresses this issue by incorporating negative gradients for rejected actions, its improvements are still limited without effective long-term credit assignments. By training a turn-level reward model that utilizes training time information for credit assignments, we see significant gains with SuiteRL, outperforming multi-turn DPO by 6% in back-end programming success and 5.4% in front-end design win rates. Notably, the SuiteRL model using LLM A3.1 to 8b instruct matches the performance of the larger LLM A3.1 to 70b instruct and competes well with proprietary models like GPT-4o and o1 Mini. We then analyze the advantages of SuiteRL over baseline models. We explore how to effectively use training time information for credit assignment through best-of-n sampling experiments in back-end programming. Here, we sample n candidate actions from a fixed LLM A3.1 to 8b instruct and apply different methods to select the best action. We compare our SuiteRL reward model with three alternatives: SuiteRL without training time information, LLM as a judge which evaluates actions based on interaction history and reference solutions, and SuiteRL with a value function that predicts expected success rates. Our findings reveal that using training time information significantly enhances credit assignment capabilities, as shown by the performance gap between SuiteRL and its variant without this information. While LLM as a judge offers some improvements, it can be distracted by response length and format rather than focusing on task success. Additionally, the standard practice of using a value function does not yield comparable performance to SuiteRL, highlighting the importance of our specific algorithmic choices. We also investigate the best parameterization choices for the critic in credit assignment. Our ablation experiments reveal that using a regression head does not generalize well compared to SuiteRL, and incorporating training time information greatly enhances performance. We find that omitting the normalization step leads to the trained actor generating shorter responses, underscoring the need for careful parameterization in multi-turn RL algorithms. Furthermore, we assess how SuiteRL scales with the amount of fine-tuning data. Although it initially requires more data to train a reliable critic compared to multi-turn DPO, SuiteRL quickly improves with additional samples, leading to better performance as the critic becomes more effective. Lastly, we explore how SuiteRL performs across different model architectures and with off-policy data. Our experiments with a stronger model, LLM 3.1 to 70B Instruct, show that rejection fine-tuning struggles with data from a weaker model, resulting in a drop in success rates. In contrast, multi-turn DPO benefits from off-policy data, while SuiteRL maintains a consistent performance gap by effectively utilizing training time information for credit assignments.